for a nice quick summary of the work.
Thank you.
Ayan, you're next.
Yes.
Yeah, so it's 13 minutes plus 2 minutes for question answer session.
Okay, thank you.
Yeah. So Ayan K. Patra, he will speak about black hole interiors as trans-IR holographic RG flow from SINP Kolkata.
Yeah, thank you. So let me first thank the organizer for giving me an opportunity to speak about my work in this wonderful conference. So title of my talk is Black Holes Interiors as Trans-IR Holographic RG Flow. This is an ongoing work in collaboration with Elena Caceres, 𝗰𝗵𝗶𝗶 Kundu, and Sanjay Shoshi. So the outline of my talk is the following. First, I will give a brief introduction and try to motivate. Then I will talk about this holographic A function. After that, I will talk about the thermal A function and about this quantum information and the trans-IR flow. Finally, I will conclude and talk about the future directions. So what we are trying to do is that we try to study the holographic RG flow in the interior of a black hole by analytically continuing the radial direction. And we know that this radial direction in the bulk theory is related to the analogous to the energy scale in the boundary theory. So in QFT, one may analytically continue a non-trivial renormalization group flow beyond its infrared fixed point to a trans-IR section of the flow by complexifying the energy. One very particularly interesting quantity in Einstein gravity that decreases along this flow is a function, and we try to give a thermal analog of this A function, and guided by this A function, we ask three very specific questions. So first one is that do the trans-IR flows obey a monotonicity condition? Second being, what characterizes the end point of the trans-IR flows? And the last being how does the trans-IR flow relate to quantum information? Before I'll address this question, let me give a brief introduction of the holographic A function. So we start with the Einstein gravity in d+1 dimension coupled to various scalar field with this following action, and this potential has a number of extrema at those points, and at those stationary points, the solution is just the radius d+1. Now let us consider a solution where the scalar sits at the UV fixed point near the boundary and makes a smooth transition to an IR fixed point in the interior. This transition can be thought of as holographic version of the RG flow, and from the boundary field theory perspective, the boundary CFT flows from the UV fixed point to a IR fixed point. Now one usually considers the domain wall unsatch for such holographic RG flow, which is given by this following metric, and one defines the A function by this way, which depends on this warp factor, and using the null-energy condition, which says that this you take any null vector when contracted with the bulk energy tensor, and one can show that this A prime rho is always greater than or equal to 0, which implies that this A function or A is a monotonic function in the radial direction. So in other words, this AUV is greater than or equals to AIR. Now, what we are trying to say is that we propose a thermal analog of the above A function, which is this we call this AT rho, and which is given by this formula, and we choose the metric unsatch to be this domain wall type unsatch, and we set the location of the horizon at rho equals to 0, and the boundary is at rho equals to infinity. Now with this function, one can show that this the thermal A function is the same for the vacuum ADS d+1 and ADS Schwarzschild, which is a consequence of the both geometries being dual to states of the same UVCFT. Now we use the null energy condition and show that this A prime rho is always greater than or equals to 0 for rho greater than or equals to 0. Now to go inside to access the interior of the black hole, one can do this analytic continuation where one sends the radial coordinate to some ik. But we find that it is computationally easier to consider different ansatz. So we take a different ansatz to show the monotonicity in the interior region. So this ansatz is deformed area Schwarzschild near the boundary, and it is Kastner universe near the singularity. So R is R equals to infinity is the singularity, and R equals to 0 is the boundary. Now, using the same null energy condition, we find that this A function, or the thermal A function, decreases along this trans-IR flow direction, which is the interior of the black hole. So we can say that this A function is a monotonic function of the entire flow, answering the first question. Now this is the cartoon for such flows. So this red, so this black arrow represents a conventional UV2IR IR holographic RG flow, whereas this red arrow indicates a trans-IR flow parameterized by a time-lag radial coordinate. Now this, if we use this, try to find this A function in the Kastner-like solution, we see that this A function, this is the form of the A function, and in the Kastner regime, where this R tends to infinity, the chi function blows up. So the chi function blows up as a for that reason, this thermal A function vanishes at the singularity. So it might indicate a total loss of degrees of freedom in the CFT state. So it answered our second question. So this is a numerical plot for the A function, thermal A function, plot with respect to the radial direction, and Phi0 by T is the deformation parameter, and Phi0 by T equals to 0 represent that there is no deformation of the CFT state. So it starts from a maximum value, and it monotonically decreases and become 0 when R tends to infinity. Now we try to answer the third question, which is that how does the trans-IR flow relate to quantum information? So we take two proposals for complexity equals to volume and complexity equals to action, and we find that in the picture of complexity equals to volume, the co-dimension one slices can never probe the region near the singularity region. They stuck at some critical radii, which I call RC, and at these late times, when the boundary range tends to infinity, the rate of change of this complexity or the maximal volume is related to the thermal A function. So this thermal A function has the knowledge of the growth of the complexity at the late time. So next thing we try is the complexity equals to action. So for the complexity equals to action, what we do is we evaluate the action on the WDW patch, and there exists this null joints which is just the null rays meeting at the interior point, interior region. So there exists some boundary time after which these null joints exist, and so this is the late time picture. There's this null joint exists, and within this 0 to TC, within this 0 to TC limit, we take this space-like symmetric geodesics, which is related to the this turning point. So what we can say is that this turning point is can be mapped to the boundary time. So we have these. For late time, this turning point is mapped to the boundary time when TB is greater than or equals to TC, and for this 0 to TC, this the interior point can be mapped to the boundary with this space-like geodesics. So one can say that these null joints are a good probe to the trans-IR flow for TB greater than or equals to TC, and space-like geodesics are a good probe when this region is 0 to TB to TC. Yes. And so the conclusion and the future directions are following. So we have constructed a candidate for the A function, which is monotonic along the entire flow, and this thermal A function vanishes at the singularity, indicating they might indicate a total loss of degrees of freedom. So the interesting future directions are following. So we can study this 18 more examples of the flows, which is the higher order scalar interaction, vectors, etc., and an analogous extension of the thermal A function to higher curvature theories. Thank you.
Thanks, Ayan. Questions, please. I think there is a question from TIF. Okay, I was just wondering, what about the...
Hello?
Yeah.
Yeah, sorry, I have a small question. So this AT quantity that you defined,
Yes.
So you mentioned something that it should correspond to in the boundary side. Could you please elaborate on that?
So this point.
Yeah, no, I mean, this AT that you identified, which is a monotonic quantity, what do you think? Yeah, what do you think corresponds to on the boundary?
Okay, so so actually this AT in the so we are probing in the interior of the black hole. So so in that sense, that so AT.
So by complexity, I thought you meant some kind of complexity on the boundary, or maybe not. I don't know.
Yeah. Sure. So the complexity at this so this AT at the evaluated at this RC just tells you about this growth of the complexity.
Oh, I see. So and then further you use this other dictionary which is proposed, which says volume should be equal to complexity, and that's how you want to relate it to this boundary quantity. Okay, I see. Thank you.
Thank you.
So, can I make a very quick comment just to so just to sort of repeat what Ayan said, I think if you take just the standard Radius-Schwarzschild geometry, this AT is exactly the central charge of the dual CFT. Nothing surprising. Even if you take empty ADS or you take Radius-Schwarzschild, it's just the central charge of the CFT. But when you deform it with a relevant operator, like what is being done here, then of course the entire geometry changes, including the inside of the black hole. So the point here is, I think, Ayan is trying to make is that there is the same AT function that you could have defined would actually have a monotonically decreasing property inside of the black hole as well, and along a direction with which you can connect features like complexity, if you believe these proposals and so on and so forth.
Yeah.
Okay.
Thank you.
So if there are no further questions, let's thank Ayan once more. Very nice.